Welcome to the HeuristicLab tutorial on symbolic regression. In this tutorial, we will cover the basic functionality for symbolic regression and for analyzing results in HeuristicLab. Symbolic regression is a data-based modeling technique which takes a simple table like this and produces a potentially nonlinear mathematical model like this. We start from a sample algorithm on the start page, for which the parameters are already pre-configured. New data can be loaded into HeuristicLab by clicking on the Import button. Alternatively, you may also select any of the available benchmark problem instances. Here I have a sample comma-separated values file containing the data of the so-called emulator problem. The first row contains the feature names, separated by a semicolon, and below all the data is stored in the same format. After this quick examination of the data, we are ready to import it. In the import dialog, it is possible to configure the value separator character and the format for real values and dates correctly. Additionally, we can select the target variable and configure the training and test partitions. For this dataset, the split is 50-50. We can immediately see if the import was successful as the problem data name changes. By double-clicking on the problem data parameter, it is opened in a new view to allow easier configuration. We quickly inspect the data by clicking on the dataset and see that it contains around 600 observations and 11 variables. In this view, we can also adjust the set of input variables and select the target variable. Now we are ready to start the optimization by clicking on the Play button. During the runtime of the algorithm, we can observe all result values in the results view, which is dynamically updated. For example, the best, average, and worst qualities are shown as a line chart. In a similar way, the variable frequencies chart shows the most frequently referenced variables in the population of models. Additionally, the symbolic expression tree length histogram visualizes the size distribution of models in the population. The most important result is the solution itself, which is stored as the best training solution result. For regression problems, the solution encapsulates the concrete model, the problem data and quality metrics, as well as evaluation results. The list of quality metrics includes the mean absolute error, the mean squared error, and Pearson's R-squared. The current best model can be visualized as a tree. Next, I will show the different options for visualizing the model predictions. First, it's possible to plot the estimated and actual values in a scatter plot. The shape of the point cloud is an indicator for the accuracy of the model. It is also possible to visualize the data for the holdout set. In the line chart, the same information is shown in a sequential order. The target values and the model predictions are plotted on the y-axis. Sometimes it's useful to show the distribution of residuals, which again can be visualized for the training partition and the holdout partition separately. Another convenient visualization is the error characteristic curve. This visualization is similar to a receiver operating characteristic or ROC curve, but works for regression problems. The area under the curve is larger for models with smaller residuals. As a reference, this visualization also shows the error characteristic curve for two baseline models. First for the constant model and second for a linear model using the same input variables. At the end of a genetic programming run, it is often useful to analyze the model in more detail and to simplify the model. This can be accomplished by clicking on the Simplify button, which opens the simplifier view. In the left part of the screen, the model is visualized as a tree with colored nodes. In the right part of the screen, the quality metrics and visualizations are shown as before. The coloring of the tree indicates the importance of the subtrees regarding the training quality. Green subtrees have a strong effect on the output, while white subtrees have almost no effect on the output. By clicking the Simplify button, the model is mathematically simplified without changing its output. For example, additions of constants are automatically pre-computed. Now it is possible to replace nodes of the tree by constants by double-clicking on them. For instance, nodes that are red or white can be replaced by constants to simplify the tree without a significant loss in model accuracy. Collapsed subtrees are indicated by an orange border and can be expanded again by another double-click. Using this functionality, we can iteratively simplify the model. The quality metrics and charts on the right-hand side are updated after each change, so the changes in quality can be easily monitored. Usually, after simplification, the quality of the solution is worse. This can be caused by incorrect numerical constants. For retuning the constants, the Optimize button can be used. In the background, HeuristicLab now uses a gradient descent algorithm to optimize all numeric constants for this fixed nonlinear model structure. When we are finished simplifying the model, we can now save the solution to a file, otherwise the changes are lost. Alternatively, we might also want to export the model to use it in other applications. For this, we use the View Host button in the top right corner of the view showing the model as a tree to switch to a different model view. The view called Mathematical Representation shows the model in mathematical notation. The view called Textual Representation allows to show the model in different textual representations, such as a simple prefix notation which is easy to parse, or as a MATLAB function, or as an Excel expression, or as a LaTeX expression to include the model into publications. If necessary, it is also possible to export the whole solution to an Excel file. This is especially convenient if you want to use the evolved symbolic regression model in your business processes. The resulting Excel file contains all quality metrics such as the mean squared error or the Pearson's R-squared, all problem data, and the evolved function as an Excel expression. The Excel file also contains visualizations of the model output in form of a line chart and a scatter plot. This concludes this video tutorial on symbolic regression with HeuristicLab. Feel free to have a look at our other video tutorials as well.